just let me start actually part with this discovery of the part atomic part nucleus. So all of you know actually before 1911 that J.J. Thomson's actually giving a part plum pudding model of the part atom, and where he have actually just have mentioned that the electrons are part simple embedded in a part sphere of positive charges. Okay, and this model could not explain the part scattering of the alpha particle. And after that, this is 1909 in George Marsden also given a part provisional or the on the part supervision of the Ernst Rutherford, that he performed the part famous this gold foil experiment, and also just he found that part some of the particles alpha particle are get recoiled back from the center of the atom, so where a heavy positive charge, because alpha particle is a positive charge particle, since it is get repelled back, so he just located that part something is part inside on the center of the part atom, so which is nothing but part maybe a part nucleus. So these results are part simple surprising, because most of the alpha particles are simple passing straight through the part foil without deflection, and few are simple scattered at a small angle, just like a part about 1 in part 8,000. And so like that, but actually this give the part actually a part location of the part nucleus inside the part atom. Okay. Now, so then after that actually just so this scattering formula actually based on is the slide is moving? Hello, hello,
Hello, sir.
is the slide is moving? Okay. So so to explain part this angular distribution of scattered alpha particle, Rutherford derived a part scattering formula, that is d sigma by d omega, and this is nothing but a part simple the part scattering formula here. So you can see that is Z square by 16 pi epsilon 0 E whole square into 1 by sine 4 theta by 2, where Z is the part simple atomic number and E is the part simple kinetic energy of the alpha particle, and theta is the part simple scattering angle. And this theoretical result was excellent in agreement with the experimental data confirming the nuclear model of the atom. Okay.
The
And
presentation not visible.
hello.
The presentation
Yes.
not visible.
Not visible.
Yes, sir. Only
Uh,
G
is
is
it now
showing.
visible?
Sir,
No,
your
sir.
screen is not visible.
I have shared now already. It's not visible.
No, sir. Before it was visible, now it is not visible.
So your voice actually is not audible actually.
Sir,
Okay,
before it
let
was
me.
visible. Now it is not visible.
Now, now not visible.
Okay, just wait. Enter screen. Is it now visible?
Yes,
Yes,
sir.
sir. Now it is
Visible.
visible.
Okay. Okay. So this is the part just simple ideas, or the part actually the pathway to how to just locate the part this nucleus inside the atom. There are part many experiments are performed, and finally they have scattered the derived the part scattering formula, and from this scattering formula it is estimated that a central heavy point is there, and that is nothing but a part nucleus. So after that so this actually this discovery of the part neutron that nucleus leads to the different features of the part this nucleus, particularly that we can talk about the stability of the nuclear stability. And in your part basic classes actually the stability of the part nucleus actually is nothing but actually it is simple describes an atomic nucleus, how it resistance to spontaneous decay and its tendency to remain unchanged. That means that when radioactive elements are part there, so they may be undergo the part spontaneous actually disintegrations, but actually stability is that factor which actually resists to this spontaneous part decay actually. A stable nucleus exists in its lowest energy state, while an unstable nucleus will undergo radioactive decay to achieve a more stable configuration. So, because a stable nucleus exists in part, because part any atom that is to be part stable, it has a part low energy, but when it has a part high energy, it may be part leads to unstable. But stability is one condition which is simple actually describes that the part is the low energy state of the part the nucleus, and which also resistant to the spontaneous decay actually. So this is the part the graph that shows actually the number of the proton in the part atomic nuclei, or the number of atomic numbers of the atoms, and this is your part atomic. This is called the number of the nucleons per atom, and this is the part stability curve for n is equal to z. This n is the part number of neutron, z is the part simple proton number, and you can find there is a part stability graph. It will be part looks like a belly like structure. Okay, so the stability of the nucleus is primarily determined by the delicate balance between the two opposing forces within it. That is a strong nuclear force which binds the proton and neutron together, and the electrostatic repulsion between positively charged proton. When the strong nuclear force is not powerful enough to overcome the repulsive force, the nucleus became actually part unstable. So that means I want to say actually what is nuclear stability. So what is the features of the part? So what is the what I can say actually the what is the requirement of the stability of the nucleus and how it is actually achieved. Okay, now so these are the different factors actually simple influencing the stability of a nucleus. Particularly, I can talk about the part neutron to proton ratio, that is N to Z ratio. This ratio of neutron to proton is a primary indicator of the part nuclear stability. So for lighter nuclei up to Z nearly equal 20 or Z atomic number equal to 20, the most stable nuclei have N by Z ratio of approximately 1 is to 1. That means number of neutron is equal to number of proton, for which you can find the ratio is 1 is to 1. For heavy nuclei, that is atomic number greater than 20, the repulsive electric force between the proton that is increases with the number of proton, and to compensate for this, that we need actually more neutron to be increase the strong nuclear force and holds nuclear together. As a result, you can find this N by Z ratio for stable heavy nuclei gradually increases about 1.5 to 1.5 is to 1. That means when N by Z ratio is greater than 1, then that is leads to the part stability of the part nucleus is part increases. But if it less equal to 1, then that is the part the nucleus is part more stable, and then if it less than 1, this is corresponding to unstable. Okay, so the band of the stability you can find when the number of neutron is plotted against the number of proton. The graph that I have shown in the earlier, the stable isotopes falls within a narrow band. Just you can see the stable nucleus are simple falls within the part narrow band here. Okay, and you can find that is called the part band of stability, and nuclei that fall outside the band. Suppose this is the part band, na? So the nuclei, the nucleus which falls outside the band. Okay, that is a simple, we can say they are unstable and undergo the part radioactive decay to adjust their part N by Z ratio towards the stable region. That means this graph actually particularly determines whether the part nucleus, so which nucleus are stable and which nucleus are part unstable, and that can be determined by the part N by Z ratio in a N by Z ratios. So when N by Z is equal to 1, this is stable. N by Z is greater than 1, this is leading to the that increasing stable, and less than 1, that is found to be part unstable, and for which you can find there are some of the part nucleus that is those are stable nucleus, they can fall inside the part valley, and those are lies outside the part valley, they are simple unstable. So now to reduce the part unstable nucleus, or those are unstable, they can easily undergo actually part this nuclear decay, and for those are part simple lying within the valley, they are part regarded as part stable actually. So in many cases that we should need actually this for any nuclear reaction, we need the part unstable. That is why we have to bombard the part this thermal neutron to the stable nuclei, and accordingly that you can find this stability curve is also part goes on part changing. Okay, Then this also another factor that is binding energy per nucleon, that you can see the binding energy curve. If you can because the binding energy per nucleon and also the proton number, if you can plot that, you can find it is simple very, but it is this binding energy curve actually but increases very rapidly for light nuclei, and peak, and you can find there is a peak around 56, that is iron, and then gradually decline for a part heavier nuclei. When you can get the binding energy curve in detail, that you can see such type of graph, will come to the latter. Then another is part called the odd or even number of part nuclei. So particularly pairing of proton and a neutron that affect the part nuclear stability, and nuclei with even number of both proton and the neutron are generally the most stable because they benefit from the part pairing effect actually. Okay, and second thing is part nuclear with even number of one and an odd number of the others are part less stable, and nuclei with the odd number of both proton and neutrons are also least stable. So you can see, so depending on whether the part number of proton or the number of neutron that is even or odd, accordingly that you can determine the part the stability of the nucleus. Second thing is the part magic number. So you know the part the nuclei with specific number of proton or neutron called magic number are exceptionally stable, and these numbers are part represent field energy cell within the nucleus. For example, the magic number of protons are part 2, 8, 20, 28, 50, 82, 115, and this magic number neutron is found to be 2, 8, 20, 28, 50, 82, 126, and 184. So depending upon the part, this number of proton and the part neutron and their part magic number, the stability can be also part determined. Then this is all about the part. This is stability. What is stability? So what is the stability responsible for? Then we can see on what are the factors that are influencing the part stability. This may be a part of a part long question. Okay. Hello. Yes.
Yes, sir.
Okay. Are all there, or that just only part on and that they leave? Hello, Firoz.
Yes. Hello, sir.
Are you
Yes,
there?
sir.
And others who are named Smita and part Nivedita, are you all there?
Yes, sir.
Okay, okay. Then let me come to the part nuclear binding energy. So you know that inside the part nucleus, you know the protons and the part neutrons are part there. But it is a very astonishing question that though the protons are actually are part positively charged, okay, and the neutrons are part simple neutrals, but how they are part bind together and they close inside the part this atom. So that we can say here, this is the amount of energy that required to bind the part nucleons, or the amount of energy that simply released during the part actually the breaking of the part nucleus, we call actually the nuclear binding energy. So the nuclear binding energy is simply defined as the energy required to break up the nucleus into constituent proton or neutron, or to separate them to such a large distance they may need to interact with each other. We call actual part the binding energy. Hence, this binding energy is the minimum amount of energy required to disassemble a system of particles into its individual component and separate them infinitely far apart. That means the minimum amount of energy required to separate the part nucleons from each other, we call actually part this binding energy. Okay, so the concept of binding energy can be understood in terms of mass energy equivalence, that is Einstein's mass energy equivalence relation, and it is seen that the mass of stable nucleus is always less than the sum of the masses of proton and neutron. Okay, and this mass difference is called mass defect, and which is this mass defect actually leads to account for your part this part binding energy. That is why we can write the binding energy is equal to delta m into c square. So the delta m is nothing but a part mass defect. Then we can go for the part expression for binding energy, that is so how we can get this part delta m into part c square, just we have written here. So if I consider a part simple and atomic nucleus whose symbol is part XZA. So let M be the part experimental mass of element. Then MP is the mass of the proton, Mn is the mass of the part neutron, and actual mass is you can find that is ZMP plus means number of proton times into mass of the proton plus number of neutron into the mass of the part neutron. So the mass defect actually is part the difference in actual mass and experimental mass we call mass defect. So the delta M is equal to ZMP plus A minus Z Mn minus your part M. And now this mass is converted into binding energy, and delta EB is equal to delta M into part C square. Okay. And delta AB, so I can substitute the value of the delta M over here, so that this is the part, the expression for this binding energy of the part nucleus. Now, if I can express in the part actually part energy in it, so I can multiply your part simple the delta M into C square, okay, by 931 by your part C square MAB, so that I can find that means if delta M given, then I can multiply 931 per MeV, then I can immediately get the part binding energy of that atom, of that nucleus. Okay, so this is the part final expression for the binding energy. Okay, now the binding energy curve per nucleon, you can see this is called the part binding energy per part nucleon, curve per nucleon. So in the x-axis that you have taken mass number, and the y-axis that you have taken binding energy per part nucleon, and you can see from this graph this binding energy curve per nucleon is simple increases for the light nuclei, but after that actually it is just having some wavy structure, and after the part iron or the sulfur you can find this is became a part stable and also stable or the part saturated. But after the part this more means uh, exactly at the part 200 atomic number or the mass number of the part some atom, and okay, so it is again a part decreases. So this is the part simple the part nature of the part binding energy per part nucleon here, and the detail what I told this is written here, you can read. Okay, now coming back to part mass defect, you can find a nucleus is simply made up of your part Z proton and n number of neutron. So if we add up the part mass of the proton and neutron separately, the total is always is part greater than that of the actual mass. Just for example, if you take actually 50 gram, okay, and that 50 gram is nothing but equal 20 plus 20 plus 10, you must find that 20 plus 20 plus 10 is not exactly equal to that of the 50, though it is numerically equal, but you can see there is some milligram difference will come. Okay, so similarly, if we can take actually the number of proton and also the part the mass each the mass of each proton and the number of neutron and mass of the part neutron, okay, so it is found to be part there is a difference between the rest mass of the nucleus and the mass of the constituent of the part nucleus. Okay, and that difference is nothing, is called the part mass defect. So the expression for this mass defect is found, you can see. So for a nucleus with the atomic number Z, neutron number n, and mass number is what, that is you can find Z plus n. So sum of the free nucleon masses when separate, or if that is if M is the part simple the mass of the nucleus, that is the experimental nuclear mass, then M nucleus is found to be ZMP plus NMN, and the mass defect delta M is the missing mass, so it is found to be ZMP plus NMN minus a part mass of the part nucleus, and MP be the mass of the proton, Mn mass of the neutron, M nucleus is the experimental nuclear mass, and often tabulated atomic value is found to be that mass of the nucleus is found to be M atom, means atomic mass minus a part Z Me mass of the electron, or you can say Z of the mass of the part proton also. Okay, so the mass defect can also be written as the part delta M is equal to ZMH plus NMN minus a part M mass of the part atom actually. Okay, so the difference in the part or in very part short we can say the difference in the part rest mass and also the part mass of the part constituent part nucleus, so we call actually part mass defect. And sometimes also we can write also part the mass of the part hydrogen atom plus that part the total mass of the neutron minus the rest mass of the neutron, that is rest mass of the part atom. So that is also called the part mass defect. Okay, so this is the part expression or idea about the part simply the part mass defect here. Now I'm coming to the part semi empirical part mass formula. Okay. Hello. Yes.
Yes, sir.
Am I audible?
Yes, sir. Audible.
Yes, sir.
Okay. So now, so this is semi-empirical mass formula. It will be important because for many cases that you have to derive the for the semi-empirical mass formula, and you have to be read careful to this. This is actually for one important question part in nuclear physics. So all of you may care to this. See, semi-empirical means actually it is a partially based on theory and partially on part experimental data or observation. It describes a part method or model that combines theoretical principle with empirical parameters, approximations, or generalization to simplify calculation and achieve the result that match observed phenomena. For example, if you are talking about a part, suppose when you can discuss actually the different model of the part nucleus like liquid drop model, cell model, okay, in that cases you have to be discuss actually your part this semi-empirical mass formula. But here is the part simple generalized formula, okay.
Okay, sir.
Okay, see, so the semi-empirical mass formula is a formula that provides a good approximation for the binding energy of a nuclide that is based on the liquid drop model and empirical data. That means here I want to say the semi-empirical mass formula is to be derived from the for this liquid drop model, and you can find this is actually consisting of the part different numbers or so different factors. Okay, so that we have to discuss. So it is expressed as sum of the 5 terms. One is called volume term, other is called surface term, then third one is called Coulomb term, fourth one is called asymmetry term, and the last one is called the part pairing term. That means when you can derive the part semi-empirical formula, you must find this is a simple combination of the part these 5 terms that must be present in the this formula. So each term accounts for a different physical phenomenon contributing to the overall stability and the mass of the part nucleus actually. Okay. Now, so how to derive?
Explain, sir.
Yes,
Could you please explain shortly what is liquid drop
I'm
model?
coming to all these terms, this volume, surface term, everything that I'm coming to here in the next slide here. Okay, just you can see. Okay, so
Okay.
the semi-empirical mass is for simple derived from the basis of the liquid drop model. I'll so in the model 2 actually there are, you have the part liquid drop model, cell model, all things are there. We'll discuss. Okay, and here you can find actually in this model means this liquid drop model, particularly the nucleons. The nucleons actually the proton and the part neutron combination are assumed to be part interact strongly with each other like a molecule in a part liquid drop. So, so when they will be part actually interact, so the interaction energy is appear due to the different contributions like surface energy, Coulomb's energy, symmetric and pairing. Okay, and that is why each and everyone have added a term to this semi-empirical mass formula. Semi-empirical mass formula is nothing but it is a simple combination of a part both theoretical and also the part experimental value. So that is why we call actually semi-empirical. And this semi-empirical formula is contributed or is get up by 5 different terms like surface, Coulomb, symmetry, and the pairing terms. Okay, and the total binding energy of the nucleus is obtained by combining all these part 5 factors to this formula actually. So first, let me talk about the part volume term. Okay, so each nucleon and this volume term actually basically denoted the part AVA. A is a part mass number, and this is called the part the volume of the part nucleus. So each nucleon interact attractively with the nearest star neighbor through the strong nuclear force. And since the force is the nuclear force, so you can read the details about the nuclear force in the second module that you can find. So this nuclear force is actually short and the part attractive. So since the force is short and short ranged, a nucleon in the interior interact with a constant number of neighbor, because every neutron is may not be part interact with the other part compulsorily. It can be only interact with the part neighbor. Okay, and independent of the part nuclear size actually. Hence, binding energy increases linearly with the part atom number, and that is why I can say the binding energy due to the volume term is found to be part AVA. Similarly, when the surface term is coming to there, so you can find that is AS, and A is a part simple mass number, and that formula, as you know, the surface area of a spherical nucleus is proportional to that of the part radius, and you know the radius and the mass number relation, that is R is equal to R0 part A to the power 1 by 3. And when you can talk about the part square, then you can find that is R square, and that you can find A to the power 2 by 3 here. That means the binding energy or the part energy coming from due to the part this surface term is simple found to be minus AS A to the power 2 by 3. The negative sign simply indicates it is attractive in part nature. Okay. Now we are coming to part Coulomb term. So this Coulomb term actually is a part also contribution due to the part the major factor. Particularly here you can find this Coulomb term actually comes due to the electrostatic repulsion, and you know the nucleus consisting of the proton and neutron. Protons are positively charged, but though they are positively charged, but they are still but combine each other, forming the part nucleon with the along with the part this neutron. Okay, but so that just why I want to say here, even if they are part positive charges, so they must be part repel, but still there is some interaction, that is crossover this interaction and binding them into a part inside the part nucleus. So that is why the electrostatic reflection exists between all pairs of the part proton, and the electrostatic energy of a uniformly charged pair of radius this that are proportional to A to the power 1 by 3 is proportional to the square of the atomic number by the part the radius, and which is nothing but equal to part j square by a part A to the power 1 by 3. Just I substitute the formula, basic formula, that is R is equal to R0 into A to the power 1 by 3. And when you are talking about the part this mass means the total mass, then you can multiply part this factor actually. Okay, so to avoid double counting self interaction expression, we are writing actually z into z minus 1. So z is nothing but the number of protons that is get accumulated or accumulated on the part surface. So that is why we are giving it part actually simple idea of the part is this is binding energy due to the part Coulomb term is nothing but part z into z minus 1 by a part A to the power 1 by 3. So these are all actually part theoretical calculations actually. Okay, then the asymmetric term is also you can find, that is given by A asymmetric into A minus 2z by square 2z square by a part atomic by a part mass number. Okay, so as you know that from the because while I discussed actually the for binding energy, we have just given the importance for neutron to proton ratio, and accordingly they contain the part the neutron and the proton number. So as this is indirectly actually connected with the part the number of proton part this neutron, so we can write actually the binding energy due to part this symmetric term is simple given by minus of part asymmetric into a minus 2z whole square by part A actually. Okay, so these are all actually part theoretical formula that we are part using for explaining the part actually your we call the part semi-empirical mass formula here. Then another part is called the part pairing term, that is delta Az. So experimentally even nuclei, that is both for n and for j are more stable, while odd nuclei are part less stable. That means I want to say here, so when that odd nuclei there, they are simple giving a part more stable nuclei rather than that of a part even nuclei. So this is simple explained by part nuclear pairing. So which nuclear is pairing the part other, that also part one of the factors that actually that decides your part is pairing term actually. Okay, 1 minute. Hello, नमस्कार.
Hello, sir.
ମୁଁ ଟିକେ ପରେ କଥା ହଉଛି, ମୁଁ ପରେ କଥା ହଉଛି ଟିକେ। Hello.
Hello,
Yes.
sir.
Yes. Okay. Huh. Is the slide is visible now? Hello.
Yes, sir. Visible.
Okay. So another term is part pairing term. So experimentally you can find that is even nuclei are more stable while odd are part nuclear are part less stable. So this is actually explained by part nucleon pairing due to the part spin alignment. Okay. And the pairing energy is simple included as your part delta Aj, and this is actually for this term that you have to remember, but this term derivations you are not keeping, only you have to derive what is empirical mass formula, and with the part contribution of each term derive the part the expression for the semi empirical formula. So this actually part this formula just for even nuclei, and that is for a odd atomic mass number, and for odd part mass number, this formula that you have to remember, and the derivations were not kept actually. Okay. And when you can combine all these part terms like pairing term, asymmetry term, Coulomb term, and also that's a part surface term, that we got the part final expression. You can see this is surface term, this is your part asymmetry term, this is your part Coulomb term. Okay. So and the pairing term. So many so all the five factors are part simple get combined, and that we can find the part the final expression for the this semi empirical mass formula. Okay. Now, what is the significance of the part this semi empirical mass formula? So this semi empirical mass formula explains actually average trend in binding energy and stability, and it also predict the value of the stability. What I have shown the per stability curve. So how it looks like a valley, and inside the valley they are on per stable, and outside the valley they are per unstable. So this can be well explained with the help of the part the semi empirical mass formula here. Okay. So there is also part some limitations cannot be explained nuclear cell, because this semi empirical mass formula is not able to explain the part this cell model, but it will explain the part liquid drop model actually. Okay. Now after that we can move to your part another term, that is what we call the nuclear size and its determination from the electron scattering actually. Okay. See, so you know that apart the different methods are part there to determine the part nuclear size actually. So out of all that are part method, one we are just following the part scattering processes. Okay, and that scattering process give the part the accurate estimation or nearly part accurate estimation of the part size of the part nucleus. So that is why we just this is the size determination will be part completely determined from the electron scattering actually. So determine the part nuclear size from electron scattering involves using high energy electron to probe the part nucleus and analyzing the resulting diffraction pattern. So particularly, so when you can want to determine the size of the nucleus, we must have to bombard the part this part some of the part what you call catalyst catalytic part particle or the part neutron to the part nucleus, so that they may be part undergoes the part scattering from the surface, and from that we can calculate the part the scattering cross section, and from that scattering cross section we can estimate the size of the part nucleus. So because of the electrons at the part left on, when you can read actually the particle and the part is the particle physics in the last part of the part the syllabus. Okay, you can find what are lepton, bosons, fermions. Okay, and electrons are actually basically categorized the part lepton, so they interact with the part nucleus slowly through the electromagnetic force, which means they sense the charge distribution of the proton rather than the total nuclear matter. So this makes it highly precise method for measuring the nuclear charge radius actually. Okay, so this is why, so why we are using or why you prefer the part electron scattering method, that is here. Okay, so just I have written actually in a precise way why electron scattering is part used actually. So so first of all we need a part probing the charge distribution. Okay, so electrons being charged particle primarily interact with the proton within the part nucleus, and this makes them ideal for mapping out the distribution of charge actually. Okay, then we are coming to the part precise measurement. The wave particle duality of the electron allows their wavelength to be turned by adjusting their energy. When the wavelength becomes comparable to size of the part nucleus, it can resolve the part nucleus structure. Okay. Then measuring charge radius, this is also part another factor which may helps to determine the part size of the part nucleus by the scattering method. And contrast to the alpha particle scattering, already I told you part in the beginning. Okay, so these are the factors which are basically responsible to determine the size of the part nucleus by the scattering method. Okay, that is why scattering method is part more vital as compared to other actually. Now we can go for the part the scattering cross section. Okay, and this scattering cross section actually for a point charge or that we are using the Rutherford's formula, that is already this formula that you know. Okay, and for an extended charge distribution, the observed cross section is reduced by a factor called the form factor. Okay, we are just including this part form factor fq mod square, but all other things actually, that means here you can find the scattering cross section due to the experimental that is given by the part other for scattering cross section into the part form factor. And what is the form factor? So the form factor is the part simple Fourier transform of the nuclear charge density, that is fq is equal to 1 by jd integration of the part rho r into e to the power I q dot r dqr, where q is the part simple momentum transfer, okay, which is given by 2p by h sin theta by 2, and where p is the part simple electron momentum. If the nucleus were pointing charge, okay, and fq is equal to part 1 means form factor is equal to 1, okay, for a uniformly charged sphere of radius r, we can write actually fq is equal to this much here. The derivation part not kept, only just you can remember here. Okay, so this is the part, the three factors which by which we can determine the size of the nucleus from the scattering formula. Another is part there also, there is the determinants of a radius also. The form factor oscillate to the part because when the charge will be goes and changing, so the form factor may be part also changes. So the first zero, that is in scattering intensity, occurs when the numerator part vanishes, because as you have already part established the part formula, when this q, so as this depends upon the q, so depending upon the part q value, we have the part that we can calculate the part radius of the part the nucleus, and which is found to be, that is 4.49 for me actually. Okay, so this is the part result that you can calculate the part or radius of the part nucleus here. Similarly, we can also calculate the part the empirical law. So you know this empirical law, that means we can calculate the part the size of the nucleus from this well established law, that is r is equal to r0 into a to the power 1 by 3, and where r0 value is part fixed, so only depending upon the part mass number of a atomic nucleus, we can calculate the size of the part this nucleus. Okay, so this is called the part radius or the part size of the part nucleus here. Now we are going to discuss actually detail about the part nuclear form factor. Okay, hello.
Yes, sir.
Just one thing, just actually in second year, how many students are there? Have any idea?
Sir, daily we used to four or five students we used to do class.
But I think I have taken the first year classes in MPH 5, so there are quite many students are there.
Yes, sir.
Oh, in second year, so you are final year, na?
Yes, sir. We are in second year finally.
Okay. Okay, okay. Then let me come to the part nuclear form factor. So this nuclear form factor actually was one mathematical function that describes how the finite size and internal charge distribution of a nucleus that modify the scattering of high energy electron that compared to a point charge nucleus. Because in the point charge nucleus, you have seen we are using the part Rutherford scattering formula, but when the charges are simply distributed over a part long in a long patch or the long region or domain, then you can use actually the the nuclear form factor actually quite help to determine the part size of the nucleus. So in scattering theory, the observed differential scattering cross section is different from that of the Rutherford prediction due to the part extended charge distribution. So what I already told, okay, and this modification is simply quantified by the form factor, that is a part FQ, and for electron scattering that you should know, this experimental differential cross section is given by, already I told you part this scattering cross section given by part this d sigma dq Rutherford means Rutherford scattering cross section into this form factor, okay, and this Rutherford formula actually contain actually one point charge, and the Q is a simple momentum transfer. Means when one of the neutron is simple get collide with the part the nucleus, then you can find there is both energy and the momentum transfer takes place, and that Q means charge actually the whatever the transfer takes place, that is given by 2p by h cross sin theta by 2, and the form factor for corresponding momentum transfer, also the part this collision of the part this neutron with the part nucleus is given by part f is equal to 1 by jd over a part rho r into I q dot r dqr. Okay, so this is the form factor form means expression here. Then, so what is the physical meaning of the part this form factor? So I think this is already part described in the part in the material given to you on your part IGNO, from your IGNO you can see. So the physical meaning of the form factor, you can find that FQ is equal to part 1, which is correspond to a point like nucleus, and FQ less than 1, that is shows suppression due to the finite nuclear size, and the oscillator means so depending upon the value whether it is less than 1 or equal to 1, we can say whether the nucleus is a part point like nucleus or it is a part finite nuclear size actually. So oscillations or the diffraction minima, because when you can perform the experimental this factor also, so depending on the location of the part this minima or the peak value, we can also calculate the part size of the part nucleus, okay, and there are some common model available, that is called uniform charge sphere of radius r, which is given by part fq is equal to 3 into sine qr minus qr. If you can differentiate this, you can get actually, okay, and experimental or Fermi type distribution are also used to present the realistic nuclear charge density. That means this is a very means this nuclear form factor can be estimated from these two formula or from these two concept actually. And so when you can we can apply also for this form factor concept actually. So this form factor helps in determination of nuclear radii from the first minimum of fq square, means that it can be determined from the experimental data, and study of the charge distribution inside the part nucleus, and important in the electron nuclear scattering and neutron nucleus interaction and nuclear part astrophysics. So this form factor has played a vital role in calculating basically the size of the nucleus and also scattering cross section, and also estimation of the part sum of the part interaction inside the part nucleus. Okay, so now I'm coming to the part this uh, after that I'm coming to the last part of the part this first model, that is angular momentum, spin and the part magnetic momentum. Okay, so coming to the part angular momentum, spin and the part magnetic momentum, these three terms actually in the nuclear physics plays a part important role in describing the part simple the characteristic of a part nucleus or the features of a part nucleus. Okay, so in the first case that you can see here, uh, yes, particularly this all the things you have to calculate for proton, the nucleons actually, the nucleon you know that proton part neutron, they possesses both your part orbital angular momentum and intrinsic spin actually. So the orbital angular momentum arises from the motion of the part nucleon in its orbit inside the nucleus, and it is simple quantized as that L is equal to, this is a part that is called a part spin, yes, you can say this is called a part orbital angular momentum L, and which is given by a part square root of L into L plus 1 h cross, and L value can vary from the part 0, 1 to data or etc. Okay, or each nucleon has an intrinsic spin angular momentum, that is S, with a magnitude of the part simple given by a part S is equal to square root of S into S plus 1 into h cross, and S is called the part this is half for nucleons. So this is called spin angular momentum, and this is called orbital angular momentum. Okay, and the total angular momentum is nothing but the spin angular momentum and also the part angular orbital angular momentum, and which is given by a part J is equal to L plus S, and each nucleon state is characterized by quantum number N, L, Z, and also Mz here. Okay. So for a nucleus as a whole, the total nuclear spin you can found by coupling the angular momentum of all the nucleons, and in even nuclei, that is Z even means atomic number even and neutron number even, nucleon spin tend to pair up, and giving you part isolated spin, that is I is equal to 0. Okay, and in odd atomic number nuclei, the unpaired nucleon determines the nuclear spin, while in odd nuclei the situation is part more complex, and that simple depends on the part coupling of the last proton part neutron. So in the simple sense that we want to say, when there is a part single isolated atom, we can just have a addition of the part this orbital and also the spin, but when there is a part simple complex system is there, that you can find that uh, that odd situation is coming, like we have to discuss about the part this coupling factor. Okay, since both proton and neutrons are part simple charged, okay, the nucleons also possesses a part magnetic moment, because as you know that so whenever the charged particle comes into existence, so there must be a part the magnetic field also come. So that is why we have just introduced a part magnetic momentum. Okay, that is given by part mu is equal to G into E by 2mp into J. Okay, so this is called the part magnetic moment, and where G is the part simple gravimetric ratio, that is called Landy G factor, and MP is the part mass of the proton, and J is the part angular momentum vector. So for free proton, that it is calculated found to be mu p is equal to uh, plus 2.79 micro s Newton. Okay, and also for a pre-Newton, mu n is equal to also minus 1.900, and where mu n, that is equal, that is E expressed by 2mp. Okay, that is called the part nuclear magneton. Okay, and thus the nuclear angular momentum and the spin play central role in determining the part actually the nuclear magnetic momentum, and the measurement of the part nuclear magnetic moment gives actually the important information about the arrangement of the nucleon, and which may validate the part the cell model. Okay, so for cell model discussion, we need actually all type of this angular momentum, orbital angular momentum, spin angular momentum, total angular momentum, then spin coupling factors, and also we can also have a magnetic moment. Okay, now so about this actually spin orbital, we have the first schematic lines and the nuclear magnetic moment, because schematic lines actually particularly well explains the part all these factors. Okay, in the nuclear cell model, the magnetic moment of a nucleus with the odd and of nucleons is largely determined by the part unpaired nucleon. Okay, and the contribution of the paired nucleon cancels out, so the magnetic moment is approximated by considering only this last nucleon. Okay, and this leads to the schematic model prediction and represents the graphically as the part schematic lines actually. Okay, so this is the part idea about the part schematic lines. Let me part now go to the part magnetic momentum operator individually. So for nucleon, you have seen when there is a charge is there is a magnetic moment, because protons are part charged particles, so they must be create the part magnetic moment, and that magnetic moment is given by a part it is coming due to the part angular momentum and also the part orbital momentum and also spin momentum, and for which you can find the mu is equal to your part GLL plus GSS. The one is contribution due to orbital and the other due to part spin actually. Okay, and for proton you can find that GL is equal to 1 and that GS value is equal to 5.59, and for neutron you can find GL is equal to 0 and GS is equal to minus 3.8. Hence, this value actually part expressed in part nuclear magneton, and that is why when you can add these two, actually that the final expression you can find mu n is equal to E expressed by part twice mp here. Now, the total angular momentum you have seen that that is J is equal to L plus S and J value is equal to L plus or part minus half, and the magnetic moment is aligned with the part simple the total with the this total angular momentum Z actually. Now, this G factor actually plays G factor of a nucleon in a state or Landau formula that you can find. This effective G factor for a single nucleon is found to be Gi is equal to Gl plus or minus Gs minus Gl by 2L plus 1. So this is for derivations. So only just you can remember only because this may be part come as a short part of a question, long question. Okay, and this plus sign is for J is equal to L plus half, and this minus sign is also J is equal to L minus L part half actually. Okay, and the magnetic moment expression is simple given by a part mu is equal to Gi J mu n, and for J L is equal to L plus half we just add this value. Okay, and for J is equal to minus half that you can subtract with the part other factors as remain as such. So now let me talk about for simple the for schematic lines. So if the predicted magnetic moments for various orbital angular momentum that is L are plotted against J, the results from upper and the lower bound that is called schematic line. So what I drawn the for stability curve, that is one is upper region and the lower region, and from that we can say that is called for schematic lines. Okay, and experimental nuclear magnetic moments are usually found to lie between what these lines, and uh, and you can find actually the configuration mixing residual interactions collective effect actually not which is not infinite part in cell model, but they can be simple determined by this uh, momentum concept actually. Okay, and particularly you can find the significance of the schematic line that particularly provides the first order uh, estimates to for the of the nuclear magnetic moment, and explains why odd atomic number nuclei have the part is you can find why odd atomic number or mass number nuclei have non-zero magnetic moment while even nuclei have nearly zero magnetic moment, and experimental comparison of the with the schematic lines validate the per cell model and highlights the where additional nuclear forces are per simple important actually. So summarily, or I can say the schematic line actually have a greater significance in explaining the different part cell model, orbital angular momentum, the different angular momentum like orbital, spin, and total angular momentum. So which is not actually explained by the part that liquid drop model. So that is why the cell drop, the cell model of the part nuclear that has the part better importance as compared to that of the part liquid drop. And because this is supported by the part many experimental and also the part computational fact, for which you can say the cell model is the part most appropriate model for explaining the part this is the basic stability of a part nucleus actually. Okay, so I think that we have finished this here part. This is the first static properties of the part nucleus here. Hello. Yes.
Hello, sir.
Huh. So we have so if you have the syllabus, you can find this is the first part we have already part completed. Then you can go for the part the next model. Okay, about the part nuclear force, so nuclear interaction, where you can see the nuclear force, two body bound state, and other things are there. Okay. Hello.
Yes, sir.
Okay.
Okay, sir.
So tomorrow you can join the part in time. Okay.
Yes, sir.
Namaste, sir. Can you summarize this session?
Hello.
You mind summarize this session?
Just I'm not getting what you're asking actually. Hello.
To say, say today's topic again in a summary.
Okay, I'll just send the for the slides. Okay. Hello.
Okay, sir, send this
Yes,
slide
sir.
and explain, sir. In short,
So
and I could not join earlier.
hello. So your
I
voice
only,
is not audible actually. Please tell me clearly.
sir, I could not join the class at that time.
So you are not
Um,
joining the part in the beginning, so that's why. But others have joined. So I can share the first slide if you can. Someone may be in. If my number is there, so you can. Okay.
Yeah, would you mind recap this, sir?
Eh? Hello?
Recap କରିପାରିବେ କି ଆଜ୍ଞା?
I'm not able to get actually what you're asking.
I'm ask, I'm asking about the today's topic to recap, sir.
ସାର୍ ସେ
Today's
କହୁଛନ୍ତି କି ଆଜିର ଟପିକ କୁ ସର୍ଟଲି କହିପାରିବେ କି କହୁଛନ୍ତି ପଚାରୁଛନ୍ତି।
ah ଏତେ ଜିନିଷକୁ ମୁଁ ଏବେ ଟୋଟାଲ କହିପାରିବିନି, just let me share the first slides, okay, that you can read.
Okay, sir.
ସାର୍ ଆପଣ କୋଉଠି ସେୟାର କରିବେ ଭେରି
ମୁଁ
ୟୁଜଫୁଲ।
ସେଇଟା ପଚାରୁଛି ପ୍ରିୟଦର୍ଶିନୀ, just if you can note my number, then you can just message, so in the text message, then I can share the slide in that, and you can share your groups, okay.
Yes sir.
My number is with you or not?
No sir, we don't have.
Okay, but my number I will message to you, okay.
In message box you will send.
Got it? Hello, have you got it?
Yes sir, I got it.
So just you text message me here. There, sorry, WhatsApp. You can give this number, then we can. I can send to you. Okay.
Okay sir, if you will send then I will send in group.
You can share it to your friends. Okay.
Okay sir.
Thank you.
Thank you sir for this nice session.
Okay.